Okay, I'm going to introduce you, Miriam. So good afternoon, everyone. Thank you for coming to our seminar monthly this semester. Our speaker today is Dr. Miriam Benisti. I hope I pronounced that correctly. She studied physics at the École Normale Supérieure de Paris in France as an undergraduate, and did her PhD in astrophysics at the Institute of Paleontology and Astrophysics in Grenoble, France. She was also a postdoctoral researcher at the Arcetri Observatory in Florence, in Italy, and at the Max Planck Institute for Astronomy in Heidelberg, Germany. So currently, she is a staff astronomer at the Institute of Paleontology and Astrophysics, and that is now at the Observatory of Côte d'Azur. Are you there at the Côte d'Azur?
Yes. Well.
Oh, that's
right now I am at home, but
okay.
But there.
Okay, and she's also a teacher at the University of Grenoble Alps. So today she's going to tell us about how to unveil the early stages of planetary formation. So whenever you're ready.
Thank you very much. Can you see my screen?
Yes.
Okay, and the pointer. Great.
Yes.
Yeah, thank you very much. So it's a great pleasure to be giving this talk here. First, I'd like to introduce my close collaborators, and in particular the PhD students or former students, which names are in blue, have contributed a lot to the results that I'm going to show. So in general, the focus of my research is on observations of protoplanetary disks, and in particular, observations that are obtained with high angular resolution. So yeah, I'm just checking the time. Yeah. So I'll first present the motivation of our observation and why we care and why do we want to have these high angular resolution observations. And in general, the revolution that we've been really undertaking since say 5 to 6 years, in the sense that we have seen that disks that we thought were very smooth structures are actually very highly substructured. And I will insist on a synergy that we can get by looking at different observations at different wavelengths and how we can learn by combining them. And finally, I will, very end of my talk, will focus on the search for protoplanets, so really young planets still in formation embedded in their host environment that we think might be responsible for these substructures. So the motivation really lies in this plot. So this shows the population of exoplanets that have been confirmed until now. So the planet mass against the separation of the planet from the star. What you can see immediately from this plot is that there is a really broad diversity in the properties of planets. Not only in their nature, for example, we have super Earth kind of planet, but we also have gas giants like Jupiter's. And we have this kind of systems where we have multiple gas giants that are orbiting really far from the star at few tens of astronomical units, and that populating the diagram here. But we also have systems that have multiple planetary systems are in a very compact and very small area, small environments within the orbit of Venus, for example. So a bunch of planets are of low mass and located very close to the star. So the question that we want to ask is, how do we get to this diversity? And do we have some imprint of this diversity already in the original stage of planet formation? What exactly drives this diversity, and is it happening at the early stage of planet formation? So this is the general picture of planet and star formation, because planet formation is a byproduct of stellar formation. So we start with a molecular cloud that collapses. And then due to the conservation of angular momentum, the material is distributed around the star, so the young star. So you have a disk in Kepler rotation, so the gas is in Kepler rotation, and you have dust in this disk as well. And you have an envelope that dissipates with time. And then when you reach the stage of what we call the protoplanetary disk, but we used to call them circumstellar disk, and sometimes now we call them planet-forming disks. So the star is at just about 1 to 10 million years old. And we think that it has already dissipated most of the infalling envelope on the star. So we're left with somehow a clean system of a young star surrounded by a disk of gas and dust, in which we think that planets are already orbiting there. So they're already shaping the disk. So we do not know exactly when planets form, whether they form at this stage or if they form earlier. And that has a dramatic impact in how we can imagine planet formation. Because obviously at this stage, there are other phenomena, other mechanisms that are occurring, like infall from the envelope, that do not happen at this stage. And then with time, after 10 million years, the gas will dissipate in the disk, and we are left with the planetary system. We still have dust, but this dust here is of second generation, so it's due to collisions between planets. And my research really focused on this stage, so the protoplanetary disk phase, between, say, 0.51 million years to about 10 million years old. So when the disk is still rich of gas. So how do we form planets? There are two major scenarios. The first one is called the core accretion scenario. So we start with very small grains from the interstellar medium, and we have to basically have this grain collide and coagulate and grow to form a millimeter and centimeter sized pebbles, and then these pebbles will grow again to form meter-sized bodies and up to kilometer-sized cores of planets, which could end up being a terrestrial mass planet. When the core is large enough, then you will accrete gas in the runaway process, and you will have a gas giant. Another way to actually form a massive planet is through the fragmentation of the outer disk regions that can be cold and massive. Then these regions will collapse and form clumps that will be gas giants. So the question is, how does these two scenarios work in practice? Do we have the conditions in protoplanetary disk to actually form through one or the other scenario? And these are the questions that we will try to answer with observations. To be able, for example, to grow efficiently from small grains to large grains, we need to have conditions in the disk where we have basically the grains that are maintained in the regions of high density. And we'll see that this is something that we would like to, and we hope to trace with observations. So the questions in general is, how do we get from a protoplanetary disk phase to this huge diversity of the exoplanetary population? And the main questions are, how exactly do planets form? Where in the disk they form? And that has, again, a dramatic impact, because depending on the location where the planets will form, for example, within the region where we can keep the water in ices around grains, or outside of this region, the efficiency of the coagulations of grains, for example, will change. So depending on where the planet will form in the disk, there will be a different efficiency for the planet formation processes. So how do planets form? Where and when? The when I already mentioned before. If the planets form in a very early stage, there are other mechanisms that might, for example, lead to additional instabilities in the disk and will affect planet formation. And once you form giant planets, for example, how do they interact with the disk? So we know that giant planets actually shape the disk, and I'll come back to this in a minute. And once a giant planet is formed, how does it influence the formation of other kind of planets? And in our own solar system, for example, we know that Jupiter has played a major role in shaping what was happening within and without its orbit, dynamically, for example. So this is an open question. And in general, the disk, if you forget about planet formation, and the disk is also an astrophysical object that evolves by itself. there are hydrodynamical instabilities. The disk will evolve viscously. The central star will photoevaporate the gas in the disk. So even if we forget about planets, the disk is evolving all the time through its own mechanism of disk evolution. And what happens in practice is that we have planet formation at the same time as we have the disk that evolves through all of these mechanisms. And these two things constantly feedback each other, constantly influence each other. So what we want to do with observations is to really try to trace all these mechanisms while they are happening. So the time of planet formation, try to understand what is actually ruling and dominating planet formation. So we want to really understand the impact of these mechanisms on the structure of the disk and their evolution. So a lot of this talk will focus on what we think are signatures, indirect signatures of planets embedded in this. So we are really looking at the stages where planets are still shaping the disk. And one of the things that the planet does to a disk, so this is a giant planet embedded in the disk, and this is the gas rotating at Kepler rotation around the star. And what you can see is that the planet, a massive planet, will carve a gap along its orbit, and that will also trigger spirals inside and outside of its orbit. And these cavities, these gaps, have a direct impact in something very simple like a spectral energy distribution. So if you look at the flux emitted by the young star and the disk, this is the young star flux, and there is some emission in addition to the young star that is due to the disk, to the dust in the disk. Now, if you carve a gap and there is a region that does not have material anymore because it has a planet, then it will basically miss some flux at a specific range of wavelengths. So this is something that we have seen already 10 years ago, that we had some of these disks that were missing fluxes, and this was already an indication for this kind of cavities or gap. So the other thing we can look for are spiral arms, as I was mentioning here. And then another kind of feature that planets would create and could be observed with our observations is what we call a spatial segregation in dust sizes. What is that? Is what once you have a planet embedded in the disk, like here, it carves a gap, you have a spiral, so this is the gas. And what happens is that it's not that you only have gas, you have gas and dust, right? And depending on the dust size, you would have a different coupling with the gas. And it's like us, for example, if we have winds outside, it will just lift some small dust, but it's not going to lift a massive rock. And the interaction between the dust and the gas depends on the density, but also on the dust sizes. And when a planet carves a gap, like here you can see in the density profile here, there's the gap here. What happens is that the small grains, so the different colors are the size of the grains, and the small grains are the red one. So the small grains, the color are the density of grains, but you can see here the size of the grain versus the radius. And what we can see is that the small grains are all over the disk because they are very well coupled to the gas, so they can flow inward of the cavity of the planet. On the other hand, the large grains, so for example, millimeter-sized grains that are here, will get trapped in the pressure maximum here and will concentrate in this region. And that's what we call dust traps. And these are maybe the regions where dust grains can grow and coagulate to form planetesimals and then planets. And what happens is that when we look at different wavelengths, as I will explain in a minute, we see different things. So if we can look at the small grains, we will see them completely all over the place, basically following the gas. And this is a simulation with the planet here. But the large grains, the millimeter grains, will all be trapped in a very narrow region. So they will look like a ring. And these differences is something that we expect when we have planets. Then when we have a planet embedded in the disk, for example, that has a very low viscosity, what we can get with one planet is that we have multiple rings and multiple gaps. So this is something we'll try to find also in observations. When we have massive planets, for example, in eccentric orbit, what we also get are regions where the grains accumulate azimutally. And that leads to asymmetries in brightness distribution. And finally, when we have a planet that is misaligned with respect to the disk, that's an example. So this is when you see the disk from the top. The planet is carving a gap and triggering the spirals. And you can see here in the bottom. This is a view from the side. So the planet is orbiting here and it's inclined. And with time, what happens is that the planet will tilt the inner disk, and you will end up with a disk in inner region of the disk that is misaligned with respect to the outer disk. And this has a dramatic impact in our observations, because if you think that you have the star here, the inner disk that is misaligned, and the star will irradiate the outer disk differently on both sides of the disk. One side will be fully irradiated and will be very bright, while the other side will be only slightly irradiated here. And then it will be, the starlight will be completely shadowed by the inner disk. So this region of the disk here will be in the shadow of this inner disk. So these asymmetries can tell us that maybe there is something in the inner disk that is misaligned by a planet. So how do we observe this disk and try to find features that will trace all these structural changes that are due to planets? So this is typical spectral energy distribution of a young star. So you have here the stellar contribution from the star itself. And then in addition to it, the emission that is due to the dust in the disk. And this is the different wavelengths regime. So if you look in the infrared regime, it's around the HK band, you are sensitive to small dust in the innermost disk region that are very hot, so about 1500 K, just at the edge of the dust sublimation. If you look in the mid-infrared regime, you will be sensitive to grains that are located in the surface layers. And now if you look in the submillimeter regime, you are sensitive to colder regions of the disk, so the midplane, and also grains that are larger, that have about the size of the wavelengths, so about a millimeter size. So the goal of our observation is to have a multi-wavelengths approach, because that way we can probe different regions of the disk, the inner disk, the outer disk, the midplane of the disk, where we have most of the density of the disk to form planets, as well as the surface here. And by looking at different wavelengths, we also probe different regime in terms of the dust grain sizes. And by doing so, we are sensitive to the dynamical processes happening in the disk, because as I was saying, the different dust sizes will not be following the gas, will not be coupled to the gas in the same way. So by looking at all of these wavelengths together, we can have a global picture of what is going on. So with ALMA, as I was saying, in the submillimeter regime, millimeter regime, you're sensitive to the large grains in the midplane. And that allows you to trace the density of the disk and its temperature. And that's where we think that most of the mass of the disk is located. And right now we have an angular resolution of about 5 to 50 million. Now, if you look at with instruments like the VLT, you can, using adaptive optics, you can look in the infrared, but you need to use a chronographic mask to mask the star, because it's really bright compared to the disk. So we're masking the inner, say, 10 AU of the star, so of the disk, so we do not know what is happening here. And what we're looking at is the small grains on the disk surface that are reflecting the light from the star towards the observer. And by doing that, we're sensitive to the disk overall structure, so the flaring of the disk, its shape, and that has very important consequences in how we want to model this disk and, in general, the thermal structure of the disk. Then if we want to access the inner disk region, we need to use the VLTI, for example, so the Very Large Telescope Interferometer. And because to look at the innermost disk region that is within 1 AU, we need to have an angular resolution of a few milliarc seconds, and that corresponds to 0.3 astronomical unit. So that's for the dust. If you want to look in the gas, you need to use spectroscopy, either in the optical and infrared, that allows you to probe the wind and the accretion in this region, or in the submillimeter regime with ALMA, and that will allow you to probe the dynamics of the disk in the outer disk region. So this is for a general introduction of why we want to observe disk and how do we want to do that. And now I'm going to show a few examples of results. So before the Eschalto observation in 2015, it was thought that disks were a very smooth structure. So really like the sketch in the slides before, a central star and a smooth disk. And now we see that basically as soon as we have a disk that is bright enough and a telescope that reaches high angular resolution, we can resolve substructures or structures. And we can see that in this disk here, all of them have substructures, such as cavities, gaps and rings here, and spirals. And these are the three main kind of features, so the rings and gaps, the spirals, and the asymmetries here. And these asymmetries can be either isolated, like this one, or associated with another kind of feature. And so far, we observed about 120 disks with a resolution of about 10 to 20 AU. And this plot shows the disk brightness versus the stellar mass and the disk size versus the stellar mass. And sorry, in orange are the disks that show substructures. And what we can see is that they are quite bright and quite large. The disks that do not show substructures are in blue, and we can see that they can still be quite bright, but what we see is that they are compact. So basically, it looks like we're still very limited by angular resolution, and that we need to push for higher angular resolution with ALMA to be able to really have a complete view of the amount of substructures that we have in disks. What we found is that we have rings and gaps everywhere in terms of radii, and also everywhere in terms of the kind of objects that we see, even in low mass objects, in stars that are less massive than our own sun, or in intermediate mass young stars, so more massive than the sun, we see the rings and the gaps. We see that they have different contrasts varying with radii, and there's no clear trend that is found in terms of these properties. The asymmetries here, for example, are actually mostly found around more massive objects, Hubble AB stars, and often within these that have cavities, which could be related to, for example, the stellar binarity of these objects. In the millimeter regime, the spiral arms are very rare. Now, if we change regime, we go to the infrared scattered light. So we're looking at the small grains on the disk surface. Again, we find that as soon as we observe a disk that is bright enough in the infrared, we will see substructures. And in the scattered light, we see that we have rings and gaps as very frequent kind of substructures, spiral arms that are more frequent than in the sun-emitter, and what we call shadows. And actually, is an interpretation, because what we see in our observation is that there is one side of the disk that is fainter than in the other side. And we interpret this as being this part in the shadow, sorry, this part in the shadow, yeah, of an inner disk here that is misaligned. And this inner disk cannot be seen with direct imaging because it's behind this chronographic mask that I was mentioning before. So far, we observed 130 disks with an angular resolution from 5 to 15 AU. And we found that nearly half of the ones that are detected have substructures. So when the disk is really bright and really large in the infrared, we do detect the substructures. But what happened is that some of the disks appear very faint in scattered light, and that is a small gallery that is ranked with brightness, infrared brightness. And that disk shows basically no infrared signal in this image, but it's one of the most massive disks in the sub-millimeter regime, is ALMA. And it's actually very large. So what it means is that this disk is what we call self-shadowed. So that's the star. The inner disk here is highly puffed up vertically because it's directly irradiated from the star. And that's by being so vertically high, it basically shadows the outer disk region. So the central star can only basically irradiate the inner part, and this outer part doesn't show up in the infrared scattered light, but it does show up in the millimeter regime where we are tracing the thermal emission of dust, large dust here, and not the reflected light. We try to categorize the substructures with other properties from the star, for example, the spectral type, the near-infrared excess, and the total mass of the disk. And what we found is that the rings here in blue are usually associated with targets that have low near-Fred excess. So basically, the near-Fred excess traces how high this inner disk is. If you have a high near-Fred excess, it means that this is quite high, because basically this dust around here, or this wall, is reprocessing a lot of light from the star in the infrared. So the ones that have rings are usually the ones that have a low near-Fred excess, or a rather normal inner disk. But the ones that have spirals, so here the green, are usually associated with Herbig-Abe stars, so more massive objects that have high near-Fred excess. So this sort of like suggests that when you have spirals, you also have an inner disk that is highly perturbed, possibly by a planet. So for example, if you have a planet that will basically steer material up such that this inner disk here will be highly extended vertically. So there are multiple scenarios on how to explain the presence of substructures. I'm really focusing on planets, but there are many other scenarios that do not involve the presence of planets. For example, hydrodynamical instabilities, gravitational instabilities, and inflow from remnant envelope, and so on. So all of this will be described in the chapter from the Protostars and Planets review series from Jehan. And one thing I would like to mention is that if the assumptions that we have in our model, for example, how we treat the thermodynamics, how we treat whether the model is 2D or 3D, will have a dramatic impact on how the substructures are predicted or analyzed. And that's something that one has to keep in mind. So I'm going to show detailed example of each kind of substructures. So this is an object, for example, where we have rings and gaps in the submillimeter regime. And I already explained that these rings could be tracing this dust trapping at the pressure maximum that could be due to a planet. So in principle, we could think that we have planets here and here, and that they basically carve a gap, and at the pressure maximum, we have trapping of dust particles here. So a way to test whether these rings are dust trapped is to look at their width. And basically, if we find that their width is smaller in the dust than in the gas, it's a strong indication that the dust particles are in a narrow region that is a trap. And these two rings correspond to these 2 points here, here, and here. And what we found in this, for example, is that in the second ring that is very narrow, this second ring could actually be a dust trap. The other one, the evidence is not clear, but it also could be that we are missing angular resolution, and this higher resolution, this ring could be made of multiple rings. The fact that the optical depths that we find of all of these rings, and these are different objects, different disks, is constant, could be due to the fact that we are already forming big planetesimals that are not showing up in the millimeter region because they are too big. Now, the same disk was observed at 2 different wavelengths with ALMA, at 3 millimeter and 1 millimeter. And by looking at 2 different wavelengths, we are able to constrain the dust size distribution. And Aníbal Sierra did this beautiful work where he constrained for this disk the surface density of the dust radially, but also specifically for this purpose, the maximum grain size. And what he found is that the maximum grain size in the second ring is higher than in the first ring, which indicates that there could be ongoing growth of grains in this second ring. And that's the one that for which we have evidence that is a dust trap. Now we also have rings and gaps in the infrared, and they are very, very useful for us because they allow us to reconstruct the 3D structure, the 3D shape of the disk. That's an example of a disk where we have multiple rings. So there's one here, and this is only half of the ring that we can see, and one's here there. And what you can see that these rings are all offset with each other. And why is that? Is because we are actually looking at the ball shape structure of the disk that is here, that is due to the thermal structure of the disk. And basically looking at this with a viewing angle that corresponds to the inclination of the disk, you would see all of these rings offset with each other. So that's something that can be done for many objects, and from which we can then reconstruct the shape. So H over R, so Z over R, the shape of the disk for many disks. Now, spirals are frequent in the infrared, and there are two categories of object type spirals. The one on the left are what we call transition disks. So they are disks with cavities. Here you can see that there is a hole, a dust-depleted cavity, and we have these two spirals here. And here, the cavities is not seen. This is the coronagraphic mask with these two spirals. And on the right, we have circumbinary disks or multiple systems. For example, here there are 2 objects, and here there are 4 objects, 4 stars. But you can see there are multiple spirals here as well. There are also shadows or break in the brightness distribution and a lot of filaments. And in general, the shape of these spirals can tell us about the location and the properties of a compound. For example, the fact that these spirals are so open compared to what we predict in terms of model of planet-disk interaction led us to think that what is actually leading this spiral is a massive planet that is located outside of the spirals. In the millimeter, we have this one case that is very peculiar because it shows these spirals in the millimeter region. So that means that the large grains are actually following this spiral arm. And what is special about this disk is that the gas intensity, so this is in the gas, you can see that one side of the disk is more extended than the other side of the disk. And this is something we explain by the fact that one side of the disk is actually higher than the other one. And this shows a very strong ongoing perturbation of the disk structure. And indeed, when we look at the velocity map, so really the velocities of each emission from the CO emission line, what we find is that there are these arcs here, this C shape, that show strong deviation from Kepler rotation. So the disk that is unperturbed around the star should be rotating in Kepler rotation. And what we find is that in conjunction with the spirals that we see in the millimeter, we have these asymmetries. And this is something that is consistent with gravitational instabilities. As I was mentioning in the introduction, one of the ideas to form giant planets in the outer disk regions is to form them through gravitational instabilities. But the disk must be very massive, so we do not have a lot of disks that we think are, at least right now, ongoing gravitational instabilities. This one is one of those. Another feature that we see in the infrared are what we call shadows. So these are example of 2 disks that show these dark regions here. Here, this is a disk that has also a cavity, and that's the coronagraph that we use in the infrared. And this is our relative transfer model that reproduces quite well the observations. And to reproduce this observation, we had to consider an outer disk that would fit this ring, but to misalign the inner disk by 70 degrees. So we used an inclination and position angle for the inner disk and for the outer disk. But to reproduce these 2 narrow shadows, what we had to do is basically to have a misalignment of the 2 angular axis of the inner and the outer disk of about 70 degrees, which is a lot. And in that case, we actually have inferred something that is a misalignment that is smaller. And how does this work? Is that you have an inner disk that you misalign a little bit. So if you only misalign a little bit, you cast a really broad shadow, and that's the case from the bottom. And if you misalign even more, then you start to irradiate the outer disk from both sides and have very narrow shadows. And that's by changing the position angle of the disk. So the geometrical factors. What we found is that we have, for some of the objects, some variable shadows with time. So for example, in this object, you can see that the shadows change with time. And with that one, it's even more critical. Now it goes slightly faster. You can see that with time scales that are very close, so to a day, the shadows are moving both in position and in contrast. We always have one shadow here, but this one here is breaking and moving around. And to interpret these 2 shadows here that are nearly symmetrical, we had to invoke the presence of an inner disk that is almost polar, so almost perpendicular to the outer disk. So we have the outer disk here, an inner disk that is almost perpendicular, that casts the 2 shadows. In addition to that, because it's moving a lot. We believe that this inner disk is clumpy and has also an inner warp that is due to the fact that the magnetic field is misaligned with respect to the disk. So by looking at the outer disk structure, we could infer the presence of something strongly misaligned in the innermost disk region that we couldn't observe with this direct imaging data. Now there's a strong synergy in using different wavelengths, as I mentioned before. And the first obvious case is that when we look at one disk at in the two different regimes, so for example, in the infrared, where we're tracing the disk surface, and in the millimeter, where we're tracing the large grains in the midplane, the disks look very different. So that's one of the disks that really looks in the infrared. You can see these bowl shapes of the overall shape of the disk. Whereas in the millimeter, we see that we have these spirals in the midplane. And in that case, even more extreme, we have these two spirals in the infrared, so on the surface. When we look in the millimeter, we have this ring and this asymmetry. So the question we want to ask ourselves is, what is driving this asymmetry of these substructures in the two different regimes? Is it the same mechanism that is creating these different substructures? And in that case, what does it tell us about the disk physical conditions? So one of the things that this synergy tells us is that there is evidence for dust grains settling towards the midplane. And that's something that we need to form this planetesimal, because we need to have this dense region of the disk where grains can grow to planetesimal. And we can see in that example here in the infrared, you see the scattered light. Sorry, in color, you can see the scattered light. I think this is in HST, so optical light probably. And in contour are the observations with ALMA. So what you can see that in the HST data, we see the full height, vertical height of the disk, whereas in the millimeter, we see something that is really, really narrow vertically. And by looking at different wavelengths, we could infer that the efficiency of this dust settling towards the midplane is very, very efficient, and that overall the vertical turbulence is quite low. We also find that some of the disks show evidence for the drift of dust grains towards the central star. And that's something that we expect when grains grow. At some point, they are slightly decoupled from the gas, and basically they are slowed down by their interaction with the gas. And to compensate this slowing down, they move inward to keep the angular momentum equal. And by doing so, they migrate towards the star. And when we look in scattered light, we see the small grains. And when we look the same object in the sub-millimeter regime, we see that it's much more compact. So this in the evidence that these large grains have actually migrated towards the central star. And what we find is that not only it's more compact, but also the location and the width, the properties of the gaps are actually very different. And that's again something that we expect when we have a planet that will, as I was mentioning in the introduction, have the large grains accumulate at the pressure maximum, while the small grains that are very well coupled to the gas, like the dust in the wind, will just flow inward, and you will end up having different gap properties. I'm not sure how much more time. Do I have 10 more minutes? Is that right?
Yes, that's all right.
And another thing that we can basically infer by the combination of observation at different wavelengths is also the gas dynamics and over large scales. So this is a beautiful example of a young science called SU Auriga that had this tail here. And this tail was observed with the Hubble Space Telescope, and more recently we observed it with the VLT sphere instrument. And what we find by zooming in this region here is that this tail is actually composed of a lot of kind of filaments, and there's a lot of spirals. And we found that there is this dark lane here. And as I was mentioning before, we interpret this dark lane as being due to the shadow, as tracing the shadow from the misaligned inner disk. So the connection we try to make is whether this outer feature and this misaligned inner disk are related. And what we found by looking at the ALMA observation is that some of this material is actually coming towards us, and some of this emission is actually going further away from us. And this actually looks like this material, this tail is actually infalling material onto the star. And if you have inflow of materials, another angular momentum, you can basically generate a misalignment in the inner disk and all kinds of substructures. So we try to search for these misalignments by directly observing the inner disk with a VLTI. And because we only have visibilities and phases, we have to use a model that's very simple, say like a ring. And we derive in some geometrical parameter for the inner disk. And then we use ALMA to look at the outer disk and derive some geometrical parameter for the outer disk. So we take a velocity map from the outer disk gas motion, we subtract a Keplerian disk rotation, and we fit the data with a Keplerian disk model, and we obtain some geometrical parameter of the inclination and position angle of the outer disk. We also have a very interesting residual map that shows that there are substructures that are non-Keplerian motions. But in this project, we focus on the geometrical parameter. So we have the one from the inner disk that we observe with the PLTI, and the one that we observe with ALMA from the outer disk. And what we find by matching these observations is that these two are misaligned by about 70 degrees. And that's exactly what we needed in our relative transfer to be able to reproduce the shape of the shadow. This is one example that combines observation from the inner disk with the VLTI, the outer disk with ALMA, and with the VLT with sphere. So we have a survey of about 20 disks, transition disks, and we found that at least 6 look misaligned. And if you just focus on the blue curves here, we can reproduce also the position of the shadows that are seen in the data. One interesting question is to ask whether it's the inner or the outer disk that is misaligned. If you think that it's the inner disk, you could see that it's a planet that is misaligned and is basically dragging along the inner disk. Or if it's outer disk, then it would be late accretion impulse, so basically another cloud that is orbiting and basically from which the star will accrete the disk with different angular momentum vector, and that will lead to a different inclination. So I've been talking about planets and their impact on the disk structure, but where are these planets? And if you take the disk substructures and model them with hydrodynamical simulation, you can say, okay, these rings are due to a planet that is 1 Jupiter mass or 2 Jupiter mass. And that way you can add more planets to your planet population diagram. And we find that the substructures could be due to low mass planets as well as high mass planets. So basically there is all of this population that we expect in this that we haven't been able to see so far. And indeed, detecting a planet in a bright disk is very challenging, just like observing a disk next to a bright star is. And these are the kind of planets mass that we expect to reproduce some structures in some disks compared to our detection limits. So from the ground, this is what we think we are able to reach, so something like 5 Jupiter mass planets. And we think that we should have seen at least some of them. But there is so far one system that is called PDS-17, which we are really sure that we have planets, because this one, for example, B, was first detected by my PhD students, and we observed it in many images and many wavelengths. This is a beautiful H-band observation. And then there is another planet, PDS-70C, that was detected a few months later in a filter around the H-alpha emission line. And that traces, the H-alpha line traces accretion shocks onto the planet. And that means that the two planets are still actively accreting. So they're still embedded. So the second one, C, is here. They're still embedded into their host disk. They're still at the late stage of their formation, but still accreting material. With ALMA, we observed the same system and found that the millimeter grains are trapped in the ring, as we expected outside of the orbit of planet C. And in the gas, we can see that there is a very clear gap around planet B. And that means that planet B is very massive. Otherwise, it couldn't carve such a deep gap in an optically stick tracer. We run some hydro simulation, including the 2 planets, and we let them evolve. And what we find is that the 2 planets enter a 2-to-1 mean motion resonance and then migrate outward. And this is an analog to our own Jupiter and Saturn pair. What we also see is that when we have the small grains in simulation, the dust grain in simulation, the large grains, which are the yellow one, are trapped in a ring as expected. And that's what we post-process. And the small grains are the green ones that actually can flow inward to the inner disk, a little amount of it, and also close to the planets. And that's where we started searching for evidence of circumplanetary disk. And this is a zoom in the cavity of the ALMA observation where we see the inner disk, the outer disk, and we had some continuum emission close to planet C. There's something too close to planet B, but it was offset with respect to the planet position, so we didn't really know. So we asked for more observation with ALMA, also to separate this little thing, to confirm and separate the little thing from the outer disk. And this is the beautiful ESO press release image that was done after our observation, where you see that there is this continuum emission close to planet C. And in practice, our observation reached a much better angular resolution. And that way we could really separate the emission around planet C from the outer disk. And that's an emission that is compact and we interpret as being due to a circumplanetary disk. We see a faint optically thin inner disk. And then the stuff around planet B is only recovered when we degrade the angular resolution. And by doing so, the only thing we can tell is that we have some extended, diffuse and faint emission, but it's really difficult to recover the morphology. And we think that we are tracing some material that is basically flowing from the outer disk towards the inner disk, maybe a spiral. But the fact that these two planets have different properties of the material around them is probably due to the fact that planet C is sitting just next to the reservoir of mass, whereas planet B is located much further in, so it's completely starved of material by planet C. So basically getting only what planet C allows it to get. So what we found by doing this analysis is that the circumplanetary disk is unresolved, so it's very compact, and it's about less than 1.2 astronomical unit in size. And that's consistent with the theoretical expectation that the CPD outer disk should be truncated at 1/3 of the Hill radius. From the flux that we derived, we only have one wavelength. So we have to assume temperature and some properties for the grain size, but we can derive an upper limit, a lower limit, sorry, for the dust mass. And in general, we found that the mass ratio between the dust of the circumplanetary disk and the planet would be about similar to what is occurring in the Jupiter satellites. I will just go to the next slide. So one other thing that is really interesting to think of is that if you have a giant planet like Jupiter that is, or Jupiter and Saturn that are carving a big gap, what is going on and what is happening in the innermost disk regions that are the regions where terrestrial mass planets are forming? And do we have enough material there to grow planets or not? And that's something that we hope to answer with more observation of the inner disk. We find that this inner disk here, this is a radial plot that shows the optical depths of the disk. And what we find is that the flux of the inner disk is really, really faint, and that we can basically reproduce it with all kinds of grains. But in general, we have very little amount of dust there. And what is unclear is whether this is small dust or large dust. What we found also is the outer disk is actually structured itself. So it's not just a Gaussian where the dust is concentrating, it's actually a peak. And within this peak, there is another, what we call shoulder, another emission that we do not know if it's another ring or not. And that could mean that, for example, there is another planet sitting around here. So these are the conclusions of my talk, is that in general, having a multi-wavelength approach is very important to be able to constrain the disk structure and looking at the dust dynamics. And if you look with high angular resolution, a bright disk, you will always see substructures from which you can infer very important information on, for example, whether the dust is trapped. The dust can grow to form planetesimal. You can also infer the temperature structure and in general, whether you have an inner disk that is perturbed or not. You can use these substructures to infer the population of planets, but you have to keep in mind that if you use a model, this is very model dependent. And in general, one key something to keep in mind is that the surveys are still very biased towards the bright and large disks. There are many open questions. For example, what are in general the substructure demographics in normal disk, in more compact disks? Do we have substructures that evolve with time, and how do they affect in general the disk evolution? And how, in general, the environment in which the disk is evolving plays a role, and what is the population of planets that is creating these substructures. So the perspectives to find planets are very, very, very rich and very exciting. First, with ALMA, we have now a large program where we want to look at all the deviation from Kepler rotation that could be due to planets. Then the James Webb Space Telescope will allow us to go deeper in terms of detection limits. So now, if we can do 5 Jupiter mass planets from the ground with space, we will be able to go down to Saturn mass planets only in the outer disk regions. And then come the extremely large telescopes that will allow us, because of the gain in sensitivity and the gain in angular resolution, to really zoom into the innermost region where terrestrial planets are forming in the similar ways we've been doing right now. And that's it. Thank you very much.
Thank you very much, Miriam, for the excellent, very interesting talk. So I'm going to stop the transmission on YouTube. So for those that are watching us, bye.